Hello and welcome to the new training video on harmonic analysis of outdoor HVAC feet, or you can say that outdoor split AC feet. We also called as an anti-vibration mount using ANSYS workbench. So in this video, we will study like how to perform the full method harmonic analysis of our split outdoor split AC fit. So this method is very useful when you are modeling the visco damping material and you wanted to perform the harmonic simulation for a particular frequency range. So we will use the ANSYS workbench to perform this simulation. So this slide represents the problem statement. So here we need to perform the harmonic analysis, that is by using full method of the outdoor split AC feet, you can say the anti-vibration mount. So you can see that this is the simplified image of your outdoor split AC. And here you can see that these are like 4 feet. So the whole unit is mounted on this anti-vibration mounts. So which basically used to dampen the vibration of this respective unit. And this is what we have considered for our particular, or you can say for our present simulation. So the damper modeling use viscoelastic material properties to accurately model the damper. Okay, so we will use the rubber viscoelastic material properties to model the damper, and for the fastener like nut, bolt and washer, we will use the structural steel. So the analysis aim to determine the behavior of the system under harmonic loads, ensuring the effective vibration isolation and system stability. So as we know that there are two different methods to perform the harmonic simulation. The first one is your model superposition method and the second one is your full method. So when we talk about, I think I have already uploaded one of the blog on our channel, our website, so you can go through that. So here like what are the key points of harmonic analysis, what are the basic steps, and then the assumption and what are the restrictions, the governing equations. Okay, so there are two different methods, the full harmonic response analysis and the second one is your mode superposition response analysis. So as name suggests, the mode superposition is based on your the results of modal analysis. So it utilizes the mode shapes to express the displacement as a linear combination of model contribution. Gives approximate solution because accuracy depends upon the what are the number of modes you have extracted. So it basically decomposes the simple problem into series of simpler model analysis. Okay. So when we talk about full, it involves the solving the system of simultaneous equational directly. So there is no pre-solved result of model analysis. Gives the exact solution compared to the approximate and supports all types of loads as well as boundary conditions. So here the entire system is analyzed together considering all degrees of freedom. So likewise there are you can go through the all the points. The important point here is like it gives the exact solution and it supports all loads as well as boundary conditions. So when we talk about even here the material is viscoelastic, so it does not you can say that you are not able to model that using model superposition. So that is why we need to use the full method to perform the harmonic analysis of any viscoelastic material. Okay, so that is why we are using here a full method. So what we can do now, we will go to the ANSYS and there we'll discuss this respective problem. So if you see that I have already solved the equation, so you just simply drag and drop your harmonic response analysis system and then you can double click on the geometry. So once you will double click, you will find that so like our model is ready here. So you will see here like we do have the 1, 2, 3, 4. So we have considered the 4 different uh, the mounts, anti-vibration mounts, or you can say that these are the fits of your HVAC. So either you can use the single model, which is the combination of your damper, your nut, washer and bolt, or you can use the complete one. Even if you are looking for to capture the steepness of your the respective unit, For example, here you can even model that. Okay. So right now we are using the simplified approach by considering all these 4 feet amper. The next thing is that to model the material properties. So I have already captured the material. The first one is structural steel, which is by default, and the second was your rubber elastic, rubber viscoelastic. So you can consider the approximate material details, like I have considered the density as 2200 kg per meter cube, Poisson's ratio as well as Young's modulus. So once you will click on the filter engineering data, so uncheck that, then you will find that the remaining your viscoelastic details. Okay, so likewise you can consider the viscoelastic rubber, or you can model this respective material. You can even choose from the engineering data from here, but I am doubtful because for the rubber you can refer to the MATWEB or matrix. I think MATWEB is there where you will find the details of this. Okay, and then you can enter that manually. And let's talk about the analysis part now. So once it is done, then let's go to the your mechanical. So you can double click over here. So once you will double click, you will find that your respective model is open in a ANSYS Mechanical. So the very first you can check the geometry. I have already assigned the material. So if you want to check, you can do one thing by display color codes. Also, you will find that, see, like this, right click, go to the corresponding bodies in a tree, and here you can assign the respective material. Okay, so at present it is the multi materials because we have used the structural steel as well as here you can see the structural steel, where here you can see the rubber viscoelastic. Okay, once your materials are defined, the next step is to create the connection. So what I am doing right now, I am using the auto connections here. So the auto connections, for example, you can see the contact between the bolt and the washer, the contact between the nut and this, the contact between the, you can say that the washer and this, and here also the washer and bolt. So likewise, you can, I'm right now I'm using the auto created a contact. So let's check once again. Okay. So once your contacts are done, then if you want to create manual also, you can create a contact or simply right click, insert and define the manual contact reason. You can click like this and here you can define, for example, I will show you here the contact between the this base and I will choose the bottom base, the second bottom face. We need a bottom face of this. Okay, do one thing, hide all other bodies, select the bottom face and apply. So likewise, you can create a contact or you can use the auto contact setting. So here basically based on your tolerance value, it will detect and it will create a contact between the adjacent bodies. Okay, all are the bonded contacts we are using at present. Then mesh, you can define the mesh. So it is a simple model. So what I will do, I will just simply put a 3 mm of size, global mesh size, or else you can give the local mesh size. For example, for this, you can define the different sizing, and for the remaining, you can define the different sizing like this. I will choose. So what are the bodies over here? 2, 3, 4. Hide here and select all. Right click, insert sizing. Okay, so right now you have the body sizing for your damper and body sizing for your fasteners. So likewise, you can define here if you want the different size. Okay, I will suppress this. I will use the global size of 3 mm. Clear this and I will generate the mesh. Okay, so you can see that you can visually review the results. So here it is not captured the properly. So if you want, you can go with the further finer mesh, or else you can do one thing. You can go here, go in the sizing, and here let me check if it is available quality, aggressive mechanical advance. So here we can choose adaptive. Let's make it no. And here, if you want, you can define the growth, your curvature. You want to capture that curvature like this. Clear the generated data and generate mesh. So I'm using the global mesh size. Just wanted to make sure. Now you can see that the fillet is captured properly. Okay. So I will just ignore this right now. I just wanted to show you. Keep adaptive sizing clear. On even you can define here, like if I can show you, select this face, go to the selection size, select all with the same size. Right click, insert, and you can define face meshing. And if you clear, generate mesh. So you have the possibilities. You can either use the, see now you can see that fillet which is capture the properly. So likewise, you can create a separate mesh for your all the fillets, separate mesh for body sizing, separate mesh for fastener or damper. Okay, I will suppress right now and I will go with the global mesh size of 3 mm. When you have the complex problem, then you can use the local sizing. Okay, so once it is done, now the next task is to apply the loading and boundary condition. So for that, the very first we can see in analysis setting, like I want, let's do one thing first, apply loading and boundary condition, and later on we will define this. So right click, insert. I want to applied, as you know that here on this respect to the whole weight is supported. So I will use right click, insert, and let's define the remote force. Either you can create a remote force or you can apply directly the remote force by selecting the all the values. So right now I am assuming that the whole weight is like you can assume 50 kg. So for that you can apply the weight. 50 kg means, for example, like 110 pound approximately. So I will apply the 110 pound in Z axis, and now I will apply this respective load into the between the frequency of 100 to 200 hertz. Here you can smoothen the solution intervals, like you can give either 70, 80, or you can give the 100, which is the correct one. So it will give the results for the 100 points. So the curve will be the smoother one. And there are two methods. Right now it will come full method by default. Okay, so you can keep this as by default. Now the next task is to apply the boundary condition. So here, as this will be rested on the bottom, so let's apply the frictionless support, and on this will be the bolted further. So I will choose all this. So in order to select all these respective faces, select with the same similar size. So right click, insert, and I will apply the cylindrical support. And here what we can do, we can fix the radial as well as axial. So axial as well as radial we will fix, and we'll free the tangential one. Okay, so now you can see that there are different loads which we have applied. The first one is the remote force between the frequency of 100 to 200 hertz. Then we have applied the frictionless support at the bottom, and then cylindrical support. Now let's solve the simulation. So in order to solve, you just right click and solve the simulation. Then it will take some time to get the result. So I do have the result for this. Let me check. Let me double click over here. So we can discuss directly the result now. So meanwhile, like if you have furthermore the complex model, so you can even apply the remaining loads, like if you have the pressure, force, remote forces, if you have bearing loads, movements. So likewise, you will find the different loads and boundary conditions in a harmonic response analysis. So now let's see if our model is ready. Okay, now if you see simulation model is ready. I have already extracted the results, so I will suppress this and I will show further in front of you. So here also you can see the similar load, frictionless support, cylindrical support and remote force. Okay, and the in analysis setting you can see that 100 to 200 Hertz and 100 intervals. So the very first what we can do, we can extract, right click, insert, and we can extract the frequency response deformation, and we will extract this deformation on the remote point. Okay, right click, evaluate the results. So now you can see that this is what your amplitude versus the phase angle. And here you do have the maximum, you will find that 11.744, and it will be, or it is like at 180 Hertz phase angle. So you can choose, you can see here on the result panel, the maximum deformation is 11.744. You have the frequency of 120 Hertz and phase angle of 180 degrees. Okay. Then in order to see that the counter plot for the same, you can just simply create a counter plot result. So what it does, it will create a counter plot. If I can show you here for the respective deformation for the highest response of the deformation which we received over here, like 120 Hertz and 180 degree. So similarly you can see here it is 120 Hertz and 180 degree. So let me delete this actually, the previous result, so that it will not be create any confusion. So evaluate the result. Now you can see now here. Okay, now if you animate, you will see that how it is showing the animation. Okay, so if you click on solution information, likewise you can see the your constant equations. So here there is one more thing, like you can define here a deformation. There are two, by default it will come deformable, but as you assume that the upper structure is quite rigid, so you can use the rigid over here instead of deformable. Okay, now the next thing is that once it is done, then you can choose the stresses on this respective bodies. Right click, insert the stress, and I will extract the stresses at the highest response, that is 120 Hertz and 180 phase angle. So 120 Hertz, and I will use at 180 phase angle. Okay. Similarly, insert deformation total. So instead of all bodies, I will choose the this one, and here also similar 180 degree. Evaluate the result. So now you can see the what is the stress on this. So the stress, maximum stress is, you will find here it is minimum actually, if it is not higher one. So you can even choose the principal stresses, and the deformation, total deformation, you can have these 15 mm. Okay, so here now we do able to see what is the frequency response for the respective direction with respect to your phase angle and with respect to your frequency from 100 to 200 Hertz. And these are the points which we have mentioned over here. These are like 100 points, so you will find the 100 points along the results. So if you put more, then it will be more smoother. If you put less, then it will be less smoother. The next you have the different result like phase response. If you want to see the deformation, so I want to see the deformation on the remote point, and like the maximum we observe at 120 Hertz. So now let's see the phase response. So you can see the phase response where it is started with respect to your input. Okay, so sweeping phase. So likewise, you can study your harmonic simulation, the very first you need to apply the load in harmonic fashion, like with respect to frequency range, your force will going to vary. Then you can extract the frequency response for a deformation, or if you want like your frequency response, your stresses. So let me, stresses will be on damper if it is good, because on structural steel I do feel that, and here it should be along z-axis. So here also it should be along z-axis. So let me do one thing, because we have applied in z-axis. So okay, so here I will use the z-axis, evaluate the result. So now it should change. Okay. Okay, so now the frequency maximum you can see that 200 Hz and phase angle of 0. So likewise you can check for each and every respective axis on which right now we have applied in z-axis. So that is why we are checking response deformation in z-axis. Similarly, you can check the phase response on the bodies where you wanted to know. Okay, so this is actually the simplified problem of harmonic analysis. So whatever the model, like whether it is complex or simpler, you can follow the similar methodology. Here you can either model the complete split AC, then create the support, model the support, use the maximum weight, you consider the maximum weight, or else you can use the simplified 4 damper, or else you can use simplified the single damper with the force divided by 4. So likewise, there are different possibilities to perform the simulation. The ultimate purpose is to get the proper result. So that's it for the present chapter of harmonic response analysis. If you have any comments, please do not forget to put into the comment box. I will try to reply as soon as possible. Thank you.